Today we are going to learn about mastering SVM Hyperparameter Tuning in Scikit-learn. In this session, we will explore techniques for optimizing SVM models using GridSearchCV and RandomizedSearchCV to enhance accuracy and efficiency. Welcome to our session on mastering SVM Hyperparameter Tuning in Scikit-learn. In machine learning, hyperparameters are crucial as they can significantly impact the performance of your model. Understanding these hyperparameters and their correct tuning can mean the difference between a mediocre model and one that performs exceptionally well. Throughout this video, we'll delve into the key hyperparameters of support vector machines, such as the C parameter, kernel functions, and the gamma parameter. We'll explore how these elements influence model behavior and how you can use them to optimize your SVM models for better accuracy and efficiency. Additionally, we'll introduce two powerful techniques, GridSearchCV and RandomizedSearchCV, which aid in the hyperparameter tuning process. By the end of this video, you'll have a comprehensive understanding of how to enhance your SVM models and apply these skills in real-world applications. The C parameter in SVM is one of the most important hyperparameters you need to understand. It controls the trade-off between achieving a low error on the training data and minimizing the norm of the weights, which is equivalent to controlling the complexity of the model. A small C value creates a smooth decision surface, while a large C aims to classify all training examples correctly, potentially leading to overfitting. In simpler terms, the C parameter balances the trade-off between bias and variance. If the C value is too high, the model may capture noise from the training data, reducing its ability to generalize to unseen data. Conversely, a very low C value might lead to underfitting. To choose the right C value, you can start with a wide range and then narrow it down based on cross-validation performance. Additionally, practical examples and experimentation with your dataset are essential in finding the optimal C value. Understanding and correctly tuning the C parameter can significantly enhance your model's performance.
Kernel functions play a pivotal role in the operation of support vector machines. They allow SVMs to perform efficiently in high-dimensional spaces without explicitly computing the coordinates of the data in that space. The most common kernels include linear, polynomial, and radial basis function (RBF) kernels. Linear kernels are ideal for linearly separable data. They are computationally less intensive and can be a good starting point. Polynomial kernels increase the dimensionality of the feature space, capturing more complex patterns. The degree of the polynomial can be adjusted to change the complexity of the boundary. RBF kernels, on the other hand, are the most popular choice due to their flexibility and ability to model complex data structures. They introduce a parameter called gamma, which we'll discuss later. Choosing the right kernel is crucial for the performance of your SVM. It depends on the nature of your data and the problem at hand. Experimenting with different kernels and evaluating their performance through cross-validation can help you make an informed decision. The choice of kernel affects the decision boundary and, consequently, the model's accuracy and efficiency.
The gamma parameter in SVM is associated with the RBF kernel and determines the influence of a single training example. A low gamma value means that the decision boundary is far from the data points, which can lead to a smooth decision boundary. A high gamma value results in a more complex model that can capture intricate patterns, but it may also increase the risk of overfitting. When tuning the gamma parameter, it's essential to find a balance. If gamma is too low, the model may be overly simplistic and fail to capture the nuances in your data. If it's too high, the model might memorize the training data, making it less capable of generalizing. A good strategy is to start with a grid of values, typically ranging from very small to very large, and use cross-validation to evaluate the performance of each configuration. This systematic approach ensures that you consider the impact of gamma on both underfitting and overfitting, ultimately leading to a more robust model. GridSearchCV is a powerful tool in Scikit-learn that allows you to perform an exhaustive search over specified parameter values for an estimator. It works by defining a grid of hyperparameter values and systematically evaluating the model's performance for each combination. This technique is particularly useful when you have a manageable number of hyperparameters and potential values. To use GridSearchCV, you first need to set up a parameter grid that includes all the hyperparameters you want to tune, such as C, gamma, and the kernel type. Then, you can run GridSearchCV using the estimator and parameter grid. Scikit-learn will handle the rest, training and evaluating models for each combination of parameters using cross-validation. Once the search is complete, you can access the best parameters and the corresponding model performance. Although GridSearchCV is exhaustive, it can be computationally expensive, especially with a large parameter grid. Therefore, it's essential to carefully choose the range and granularity of the parameter grid to ensure efficient use of computational resources.
RandomizedSearchCV is an alternative to GridSearchCV that offers a more efficient approach to hyperparameter tuning. Instead of evaluating all possible combinations of parameters, RandomizedSearchCV samples a fixed number of parameter settings from specified distributions. This method is particularly advantageous when you have a large number of hyperparameters or when exhaustive search is computationally prohibitive. To use RandomizedSearchCV, you define a parameter distribution for each hyperparameter, specifying the range and probability distribution for sampling. You also set the number of iterations to control how many parameter combinations will be evaluated. In practice, randomized search can lead to faster convergence towards optimal hyperparameters with significantly less computational overhead compared to grid search. It is especially useful when you have limited time or resources. Implementing randomized search in Scikit-learn is straightforward, and it provides a highly flexible and efficient way to explore the hyperparameter space, making it a valuable tool in your machine learning toolkit. Comparing model performance before and after hyperparameter tuning is a crucial step in the machine learning workflow. It allows you to quantify the impact of tuning on the model's accuracy and efficiency. Start by evaluating your baseline model using default hyperparameters or an initial guess. Record key performance metrics such as accuracy, precision, recall, and F1 score. Once you've tuned the model using grid search for randomized search, assess the performance of the best found model on a validation set. Compare these metrics with the baseline to determine the extent of improvement. Often, visualization tools such as confusion matrices, ROC curves, or precision recall curves can provide insights into how the tuning process has affected model performance. It's not uncommon to see substantial gains in accuracy and efficiency after careful hyperparameter tuning, highlighting the importance of this step in the model development process.
Overfitting is a common challenge encountered during hyperparameter tuning, particularly when the model becomes too complex and captures noise from the training data. To avoid overfitting, it's crucial to implement robust cross-validation techniques. Use k-fold cross-validation to ensure that your model's performance is consistent across different subsets of the data. Additionally, consider implementing regularization strategies such as adjusting the C parameter to penalize overly complex models. Be mindful of the metrics you choose for evaluation. While accuracy is important, other metrics like precision, recall, and F1 score can provide a more comprehensive picture of model performance. It's also beneficial to split your data into training, validation, and test sets to ensure that your model performs well on unseen data. By following these practical tips, you can enhance the robustness of your tuning process and develop more generalizable models.
In conclusion, mastering SVM hyperparameter tuning in Scikit-learn is a valuable skill that can significantly enhance your model's performance. We've covered key concepts such as the C parameter, kernel functions, and the gamma parameter, and explored powerful tuning techniques like GridSearchCV and RandomizedSearchCV. By understanding and applying these concepts, you can optimize your SVM models for accuracy and efficiency, making them more suitable for real-world applications. Remember, practice is key to mastering these techniques, so I encourage you to experiment with different datasets and tuning strategies. Thank you for joining this session, and I wish you success in your machine learning journey.